Hi, everybody. I'm going to explain the difference between nucleophiles and electrophiles in this video. So these are going to be concepts that we use the entire year of organic chemistry. So they're really, really key in trying to understand how things are working here. So it's important to remember that nucleophiles, we're talking about electron-rich atoms. So where are our sites of high electron density in a molecule? Those are going to be nucleophilic sites. Okay, so we're looking at something that can share electrons. It's got a lot of electron density present. We're looking for those kind of negative charges, delta minus charges. That's going to help us try to identify those nucleophiles. An electrophile, on the other hand, keep in mind it's like electron lover, right? These are things that are electron poor. It wants electrons. Okay, so that's going to be something like positively charged atoms, delta plus atoms. Those are going to be electrophilic sites that can be attacked by a nucleophile. So organic chemistry, probably about 90% of it is actually just like plus and minus are going to come together. Okay, so we're looking at plus and minus reacting. Okay, the positive side is your electrophile, the negative side is your nucleophile. So being able to identify those pieces is going to be really key in helping us understand reactions. Okay, so how we go about identifying electrophiles and nucleophiles is we really want to be looking for polar covalent bonds. Okay, so remember back at the beginning of the semester, we brought in polar covalent bonds and we kind of said, oh, well, this is more electronegative, this is less. Who's going to be holding the electron density? That's going to really help you identify those nucleophile and electrophiles, okay? Resonance is also going to be a very good friend here. So we're looking for delta minus, delta plus. That's also going to tell us where our electron density tends to sit in a molecule, okay? So let's just look at a couple of examples here. So for nucleophiles, there's a ton of nucleophiles out there. But one of the things that you'll kind of pick up on just from a lot of practice is a lot of nucleophiles are negatively charged. Okay, so look for stuff that has a negative on it. So things like sodium hydroxide. Okay, so sodium hydroxide is one. Various alkoxide anions. Okay, R is going to be some kind of carbon. So this is basically just a deprotonated alcohol. Okay, and when we look at these, I want us to think OH minus with a sodium counterion. Okay, so this sodium can be whatever. It can be a potassium, lithium, whatever counterion you want. The important part is this part right here. Okay, that is showing you, yes, I have something that is very electron rich, then I have something that's a nucleophile. Okay, and it's important to keep in mind that nucleophiles are often bases as well. Okay, so we'll see a lot of overlap between nucleophiles that we use and bases that we use. And I'll make sure to point out when we have something that's not very basic, but is a good nucleophile. They do pop up and we're going to be talking about that more later. Halogens are also nucleophilic. Okay, so any NaX type of situation where X is going to be chlorine, bromine, iodine. Thiols, so deprotonated thiols. And again, and as soon as you see the sodium or any kind of counterion from the left side of the periodic table, think about that as being positive and then the thing attached to it being negative. And that's the important part here. You can use alkenes. Okay, alkenes can be nucleophiles because we have a pretty good chunk of electron density in that alkene. And then we can have some weak ones like water or alcohol. Okay, and these are going to be weak nucleophiles. And they're weak because we don't have as much electron density kind of shoved onto those oxygen atoms because they're neutral. Okay, so if I'm looking at the difference between water and sodium hydroxide, we've got a negative charge localized on that oxygen. Here, it's neutral. It's a much less reactive type of situation. So that nucleophile is going to be less strong as it would be in this case. Okay, so for electrophiles, there's also a very good amount of electrophiles here. So one of the ones that we'll be working with a considerable amount is going to be alkyl halides. Okay, so X here is going to equal chlorine, bromine, iodine again. Most of the time, we're not going to be including fluorine. It's just not quite as good for a lot of things because it's so small and so hard. So alkyl halides are going to be a really good selection of electrophiles. And we want to think about that as, yes, we do have an alkyl halide that's negative, but that carbon is positive, okay? So the carbon that's attached, remember we've got that polar covalent bond right there, that carbon is delta plus, making that an electrophile, okay? So it's important to note that the halogen here isn't really going to want to be a nucleophile because this halogen doesn't want to share its electrons, right? So the halogen does not want to be making two bonds and becoming positively charged. So it's much more likely for this to react as an electrophile, and then we can have something that comes and attacks here, and then we can use our alkyl halide as a leaving group to push off, okay? Other ones are carbocations. So we've seen a little bit of that so far, right? Where we actually have a positive charge. And then carbonyl groups. Okay, carbonyls are a huge, very important class of electrophiles. And at first glance, you might not think that they're very electrophilic, but keep in mind that we have a delta minus up here and a delta plus up here. That's just from the polar covalent bond. But we also want to consider the fact that we have that resonance structure for all carbonyls. All carbonyls can do this, where we can move the pi bond up onto the oxygen, and then we make that carbon positive. Okay, so this is significantly more electrophilic than something like a carbon attached to an oxygen in an ether, for instance, right? So that's going to be another good electrophile that we can use. We will learn more nucleophiles, more electrophiles as we go. These are the ones that we're going to use a lot this semester. But just keep in mind that the nucleophiles, they're going to be the negative things. Electrophiles, we're looking for more positive atoms, okay? So just keep that in mind. That's how we want to be splitting stuff up. This table and this table are going to grow. This is only limited. But it's going to be really helpful if you can think about polar covalent bonds, who's holding the electron density. The person that's holding the electron density is going to be your nucleophile. Something that is electron poor, that's going to be your the atom that's holding the electron density is the nucleophile, and the one that is electron poor is going to be the electrophile. I was just worried that I said that wrong. Okay, so again, as always, let me know if you have any questions, and I will see you all later, and we will keep talking about this stuff.